Firstly, right, what the fuck? Secondly, over 250,000 of you bastards watched the last video. What's up with that, Why do you want to know how to make malware so bad, huh? You wouldn't be interested in doing something illegal, would you? Of course you wouldn't, which is why, disclaimer, in this video, we are actually going to be executing some quote-unquote malicious malware. Because of that, I must once again proclaim that this video is strictly for educational purposes. YouTube did not have a problem with the last video, because again, it was just the fundamentals, nothing malicious actually happened. But today we're really testing our luck, because today we're actually going to be using actual shellcode to actually inject into an actual process. Actually, if you decide that one day critical thinking is overrated and for losers, and use this against someone or something you don't have permission to do so, first of all, good luck getting any of this heavily signatured ass shellcode to even compile. And even if you do get it compiled, running this in any half decent environment will instantly get it caught by Defender or any EDR or antivirus in this state. And secondly, that's just not cool. And it's on you if you decide to do that. I personally couldn't give less of a shit if you decide to not heed my warnings and decide to use this maliciously and end up getting arrested. This is strictly for educational purposes. Let's get on with the video. By this point, you should know what handles, processes, and threads are. You should be at least a little comfortable with the Win32 API. You should have been able to successfully create a process or message box. If you don't worry, just go watch the first video and we'll wait for you to finish. Go on. The rest of you rejoice, today is the day. For this video, I'm going to be programming and executing all of this in a virtual machine, specifically Windows 10 version 22H2, build 19045. Bro, why are you telling us your operating system's entire government or should name just say Windows 10? Listen, you water skimming lizard. Yeah, it's true, for this technique, knowing the build version or whatever isn't going to be necessary, since the Win32 API will be handling all of the overhead for us. But I want to get you guys into the habit of at least being aware of these things, since as we'll see with the relatively more advanced techniques, your OS version and build will genuinely matter. I'll be programming in Visual Studio, and in the last video I got a plethora of comments regarding what themes and extensions I use for Visual Code, which is what I was using there, not Visual Studio but Code. And I've pinned a comment with the extensions and everything that I use for weeks now, and I'm still getting comments about, are you guys' eyes painted on or some shit? We'll also need to use MSF Venom or something else to generate our shellcode. I mean, you can make your own if you want to. The one thing that you cannot do is go out onto the internet and grab someone else's random ass shellcode and just think that it's okay. Listen, this is shellcode, okay? We're dealing with serious stuff here. Don't just risk that. So for the shellcode generation part, I'm just going to use my Kali machine. I'm not going to be covering how to install or configure Visual Studio or the virtual machines or Kali or whatever, because there are almost an infinite amount of resources for you to learn how to do that. But do note that you do need something to program in and something capable of compiling your code. You also need a way to generate the shellcode. So those two and the previous knowledge about the process handles, threads, blah, 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 the Win32 API, those are absolute prerequisites that you will need before attempting this. I was also getting some questions about if knowing C, C++, C#, or whatever was necessary. Guys, your programming language is just a tool for you to do a certain thing. It literally doesn't matter. Each language Speaking of language, I should actually probably learn one. Each language has its own pros and cons, especially in its applications as it pertains to malware development. But just because I'm doing this in C or C++ doesn't mean that you have to do it in C or C++. Of course, this series is primarily going to be focused on those two languages, but you can do this in anything you want. When the first video came out, in my Discord server, which you should, again, join by the way, I was seeing people doing it in Rust, in Python, in ritualistic Gaelic incantations. So seriously, don't let the language be a barrier or a gatekeeper here. I'm just trying to teach you the underlying idea of these tasks. And one last thing, I promise. I need to drive this point home, okay? It's late for curfew. I'm not this person in the video anymore. I'm more muscular now. I mean, I've taught myself to program in C through doing malware development, and as such, my coding practices have gotten a little bit better and better the more I start doing more and more techniques. However, I am not some sort of expert in C, C++ programming, or malware development. Not even close. I would never ever claim to be. I'm literally just the most average dude with a computer and an internet connection. I'm simply making these videos as a way to consolidate my learning and to potentially teach you guys something or help you avoid certain pitfalls that I've faced during my learning so that you can bypass them. The best way to understand something, to truly understand it, is to teach it to someone else, and that's what this channel and the blog are all about. So once again, if I make a mistake, I'd urge you to postpone that little brain aneurysm that you're having and take a deep breath and let us know in the comments, okay? Okay, let's discuss process injection. Okay, well, before we even write a single line of code, we have to understand what the lore behind this technique of exploitation is. What exactly is process injection? Well, that's a pretty complicated question. First we must define what shut up. It's literally when you just inject something that you want to be ran into a target process. That's it. Yeah, the rumors that you heard during recess are true. There are multiple little variants of this technique, and the ones that we're going to be focusing on today are arguably the easiest to do so far. And another little side note, yes, we are still going to be using the Win32 API to do these injections for now. Eventually, we'll try to remove as many wrappers or high-level abstractions in our code to make it less detectable. For instance, in the next video, we'll be discussing using the lower level NT API and system calls to execute our tasks. But keep in mind that just doing this wouldn't be enough in the modern day to make undetectable malware. You have to remember that making your malware stealthy or undetectable is not a singular technique sort of deal. Most of the time, it's multiple techniques fusion danced together. Because we're just starting off, and this series builds on the previous episodes, we're doing Win32 API for now. Moreover, the subsectors of this technique that we'll be executing today is going to be shellcode injection. Here are the steps once more, and I'll even tell you the API functions we're going to be using to do this just because I like you so much. We start by getting a handle on either an already existing process or a process that we've created. This can be done with open process. We then allocate some memory into that process's memory, that memory being our shellcode that we'd like to be ran. We can do this with virtual alloc. We then actually have to write that into the process's memory. We can do that with write process memory. And finally, we create a thread to run our payload with create remote thread. And lastly, we'll be delving into doing a DLL injection, which is pretty much the same steps as the shellcode injection, except we're loading our own library into the target process, which again just runs our own code. In this case, it will be running a handcrafted DLL made by us. I like the approach of opening a handle to an existing process, since it's a bit less suspicious than just spawning one solely to run our payload, whereas with our approach, we're injecting into an already existing process. However, note that again, we are not worried about evasion for now, so you can 100% do whichever you like. This is disgustingly oversimplified, gross, right? But we'll move on to the deets once we get onto the respective sections of this video. Speaking of which, let's finally start our trek. So you guys remember that whole thing about a process having virtual memory given to it, or its own virtual address space? Well, the purpose of this technique is to allocate our own little section of memory in that target's process virtual memory space, with the necessary permissions, which we'll discuss later. This memory that we're going to be allocating is just going to be our payload, id est, our shellcode. There's a lot to uncover here, but let's just remember the steps needed for this method to work, and then we can delve into the hyperfine print as we're doing it. So let's set up the code for this technique. We'll leave generating the shellcode for the last step. There are some things that we need to make sure of. Number one, make sure that if you're injecting into a 64-bit process, you compile a 64-bit program. This will save you a ton of potential headaches, as you'll see in the common pitfall section. Number two, we need to either disable Windows Defender or create an exception for the folder that you'll be making all of this stuff in. We'll start by opening up Visual Studio. Load, holy f. So I got a comment that said I wasn't funny, so you and me, we're just gonna have to be like all serious starting now. You're lucky I just got finished doing my Tai Chi and I'm feeling particularly zen right now, otherwise you'd be in a lot of trouble. Create a new project. Let's just make an empty project. And then you want to name this something meaningful, something important to you, something very dear to your heart. And as you can see, we are very serious. I've named this Vine Boom Funny Meme. It's not funny, so let's just go ahead and hit create. Okay, we've created the project and now we actually have to add in our source file, which is going to be holding all of our code. Okay, this is unironically a horrible naming convention, dude. Obviously with yours, make it serious. I'm just being an idiot. But with our file created, we can now include the Windows header, which will let us interact and use the Win32 API, which if you remember from the last video, the Win32 API is just an interface for us to communicate with the operating system. And because I like to make my programs more verbose than they actually should be, we're also going to include the standard input-output header as well, so that we have access to things like printf. You know, now that I think about it, I only ever make C++ files, but I only ever program in C. So now I'm just going to create some status symbols so that, you know, our verbosity is a bit more orderly. Now, you could do it like this. There's nothing wrong with this. I'm just doing this so that it's more visual for us when our program runs. You can do it like this, or you can do it with like macros like this. Shout out to Baki and Aqua, by the way, for introducing me to macros. Or if you don't want to, again, you don't have to. Do whatever you want. Let's just set up our main function and test it with something random just to make sure that everything's working. Remember from the last video that this literally just means 0, but I like to be extra and verbose in my code wherever I can be. So I know probably going to save you some time to just literally do this, but again, do whatever you want. And let's just try a quick little print just to make sure that our code's working, everything's working. As we can see, everything's working, so now we can begin programming. So if you remember, every process has a process identifier or a PID, which is always a multiple of 4 if you've ever taken the time to look at it, which isn't important, but it's still pretty cool to know, and it's just because of code reuse and some other backend kernel stuff as well. So the thing with the PID is we want to be able to supply a PID through the command line so that it's easier for us to inject our target process. Otherwise, we'd have to change the PID in the source code, and processes are always closing or opening all the time, so we'd have to edit the PID and recompile, and that's just a straight-jacket padded cell nightmare. So let's instead just create a PID variable, and it's going to be of the D word type. Ooh, he said the D word. Sorry, excuse me, I have drain damage. So if at any point you don't understand where one of these data types, like the D word data type, is coming from or what it is, especially because Microsoft is trying to set like a world record for the amount of data types it uses or some shit, fret not. In Visual Studio, you can just hold down Control and then press on the data type or functions or whatever, and it'll open up the instance in which it is declared or defined. So we're holding down Control, we press on D word, and we can see that it is an unsigned long. That's what D word is. So because it's the same, we could also just do this. Right? But there's already a data type variable for this long ass one. So this is one way to look at where it's defined. An easier one is just by searching it up on the MSDN. Remember? We just discussed how detailed this holy grail of documentation is. And a neat thing you can do is save it for offline use by hitting this tiny little download button right here. Download PDF. As you can see. And once you download it, voila, your own little offline MSDN you can use for reference. But note that this doesn't download the entire MSDN, it's just for what section you're currently looking at, but it's still good to know. Anyways, you can see that it's also here, and it tells you more information rather than just looking at where it's defined in the header file. The D word, it's 32-bit, unsigned integer. Anyways, back to business. And the reason we're making this D word is because that's what open process expects from us. Let's make sure that the program is being supplied with an argument for this PID. If not, then we're going to print out a usage message so that the user knows what to do and exit with an error. And a thing I've started doing more and more is after defining a variable or declaring it, I start initializing them. So in this case, we're just going to initialize our PID to null, and it will be filled with something useful later on, but when it's declared, I want it to be initialized, and we're just going to set it to nothing for now, but at least set it to something, you know what I mean? So let's set up the PID supplying part. Oops, got rid of my freaking status symbols. So over here, what we're doing is we're checking to see the argument count. If it's less than 2, then we print out this error message, and then we return a 1, which any non-zero integer usually signifies some errors, and that's what we're doing here. Again, you don't have to use exit failure. I'm just being extra once again. So that should work, and now if this condition is passed, we can assign whatever we supplied into this PID variable. Let's do that real quick. So if the program has been supplied with the PID, then we can convert that input into an integer with the a2i function. And again, from holding Control and pressing the function name, we can see, although it looks kind of crazy, this just takes in a string as input, which is just going to be the first argument from the argument vector. And it's not 0 because argv0 is always the name of the program itself. It goes like this, right? That's what we're doing here. And let's just do a quick little print statement to let the user know that we're going to try getting a handle to this process pointed to by this PID. The reason we're doing %LD is because that's how you format a double word. Format specifier for the long is an L. If you want to print it into decimal format, we're going to do LD for decimal. And so let's run this and see if this is working as expected. We can compile with Control F7, or you can just go straight to build, compile, and then we're going to start without debugging because we just want to run this. So we can do Control F5 or just start without. And if you weren't in full screen, there'd be like a green YouTube play button that you can press on. Start without debugging. Alright, it's working perfectly. After we compile it, Visual Studio will try to run the program, but it doesn't run it with any arguments. It just literally tries to run the program. And because of that, no PID argument was supplied, and we get that error message, and it exits with exit code of 1. Signifying failure. But if we try to do this ourselves, Control tilde to bring the developer shell. Same error message. Let's try a random. Okay, it's working as expected. Perfect. For the next section, we are going to get a handle to the process now, to which this PID belongs to. We're going to be doing this with open process. So let's go look at that real quick on the documentation. So from the documentation, we can see that if the function succeeds, the return value is an open handle to the specified process. But if it fails, the return value is null. And we will be combining this with getLastError, but that's soon to come. We can see that it returns a handle. So in our code, let's set up a variable that can hold this. Just a little spoiler alert, we're going to have another handle, or another variable that's a handle, called hthread for when we eventually create our thread. So let's just also include that here while we're already doing this, might as well. And if you've watched the last video, you should know why we put this H here. It shouldn't be that much of a mystery anymore. We know that Microsoft does this well because they use the Hungarian notation naming convention. So they will put the type of a variable, whatever it returns or whatever it is, as a prefix before the variable name. If we had a bool like this, we would put b in front of it to indicate that it's of the type bool. Quick little recap. With the handle variables created, we can now use the open process function. And as always, we will go through all of the parameters that this function takes one by one, just so we have a complete understanding of what exactly this is, what it expects, and what it returns. Because this returns a valid open handle to the process that we're trying to target, we want our hProcess variable that we just created to hold the return value of this function. So the first parameter of this function we can see is the desired access, and it's of the type dword. Let's go back to the documentation and look at what this is. We can see that the desired access is the access to the process object. This parameter can be one or more of the process access rights. And if we take a look at what these rights are, we can see what exactly we can supply as an argument to this part of the code. So basically, long story short, all this is what we are allowed to do process-wise, what access we're given. The access rights that we choose here will determine what exactly we're allowed to do with the process once we open a handle to it. We can see that process all access is all possible access rights to the process or the object. I just took in, there's no space here. But typically, the easy way is just to make this value process all access, and that actually might be what we do. But typically, it's always best to give yourself the minimum amounts of rights or accesses that will let you do what you're trying to do, rather than giving yourself all access or something like that. Just as a side note, it's less suspicious that way, and it's also better practice that way. But we can see why these access rights is necessary, because let's take, for example, let's say we want to eventually, which we're going to do, we're going to write to the process memory. We would need, at least at the very minimum, we would need process VM write. We would need to supply this. This is what we'd have to supply here, because it's required to write memory in a process using write process memory, which is a function we're going to be using soon. But there's also process VM operation, virtual memory operation, which is required to perform an operation of the address space of the thing. So basically, this is just letting us tinker with the process memory. So we could supply this instead. There's a lot of these, and as we can see, if a process is protected, we are not allowed to specify these access rights on a protected process. We will get an error, but that's besides the point. Basically, what this is what we're allowed to do with the process. So for now, let's just do process all access again. Right now, we're not worried about anything crazy. Let's just get on with the code, right? We know the desired access level that we want for our process is all access just for now. So let's do that. And do note that there are more of these access rights. They don't just pertain straight to processes. We do have the same thing for threads as well, as we can see here. Look, same thing, thread all access, right? Now you know what these things are. The next parameter is a Boolean type, and it's asking us if we want to inherit the handle. Basically saying that if this process that we attach to spawns any other processes, do we want to inherit that handle? Do we want the handle value that we have here to inherit that? We don't care about that, so we're just gonna set this to false. And lastly, this is our PID. Our process ID. It's named differently, but I told you in the beginning when we started this series that you will see things named differently, but as long as you get the general idea, you should be fine. So this is where we supply in our PID. And because we know that open process returns either a valid handle or it returns null, if there is no valid handle, we can write an if statement to see if what we supplied was okay or not, if we got an actual handle to the process. If not, then we will print out the error that we got, and we'll let the user know, and we'll exit with the failure. Otherwise, we'll print out the handle that we got. So let's do that real quick. If you remember, I said that we were going to use the getLastError function eventually, and this is where we're going to use it. So what we're doing right here is putting in our little stats symbol. We are saying we couldn't get a handle to the process, and then this part is, I really like this part. I like this function a lot. Just note that if you are working with the NT API or syscalls or anything with the NT status stuff, which we'll get into later, you wouldn't want to use this because that sector of thing has its own little return values like NT status, success, or whatever. But for us right now, this is perfectly fine, and it's actually what you're supposed to do. So if we look at getLastError on the documentation, well, right now we know that firstly it returns a D word, which we're printing out here in the decimal form. Let's look at the documentation. So the getLastError function, it just retrieves the calling thread's last error code value. That's all it does. If something fails, it will spit out the error code corresponding with that failure. What it spits out is dependent on the type of error we get, which we can then cross-reference with this section here, and we can see there's a ton of these. So let's just try real quick to do two separate things. Number one, let's save this and compile it. The first thing we'll look at is if we supply some random thing in. That's obviously not a real PID. Let's try that. Look at that. Firstly, we see that we get our expected output, which is great. This is fantastic. That means that this part's working. We get an error of 87. So let's look at what that error is. And because we saw that it was 87, we know that it falls in the first range from the codes of 0 to 499. And let's go look for 87. We get an error, invalid parameter, which means that the parameter is incorrect. That is a ton of information given to us. And obviously you do not have to have this in your code, but when you're first starting out, having little debugging things like this is so immensely helpful. Let's try another one. Let's say we want to try to open a handle to a process that we don't have permission to do so. Say like we are our user, but we try to open a handle to a process owned by system. Let's see what error code we'd get then. So first let's find one of these privileged processes. Okay, so it's owned by NT authority system. This is just a system process, which is always going to be 4. As far as I'm aware, it's always 4. So yeah, we don't have access to this. This is owned by system. The highest, this is like the root user equivalent on Windows. You should know this. Let's try opening a handle to the PID of 4. We get error code 5. Let's go look at what that is. We get an error access denied. So yeah, as you can see, this is very, very useful for us as beginners starting out, or even just as we continue along. Having this kind of information can save you a ton of nail biting and hair pulling and desk face smashing. This is a little bit of a tangent, but I do want to introduce you to some of these cool functions as I come across them as well. Also note that even if you set your process access rights, this value, to a process all access, you're not going to be able to magically be able to access or alter a process that you don't have permissions to do so. This name is a bit misleading, but it's for the specific process you're actually allowed to hook onto. So if you try to get a handle to a process owned by system, as we saw with like process all access, you're not going to be able to just magically do that. You will get an error access denied error, which we saw. We could talk about debug privileges and all of that, but it's out of scope for this video. And yeah, and also there is a bit of a debate as far as I've seen on what to initialize your handle values with. So I've seen them initialized with null, and I've also seen them initialized with, hold on, first of all, and I've also seen them initialized with invalid handle value. Now, there's some lost lore on which constant or value to use to initialize your handles, but TLDR, it's a bit historical and convoluted. I'm just going to be using null. It just works better for me as well, especially with all of these functions that return null if they fail, so that's what we're going to do. But I have seen this done before, and as far as I've seen it, there's only like one function that actually uses it primarily, something like create file or something, but I'll have to check up on that later. Okay, we have opened a handle to the process at this point. What do we do now? Well, now we have to allocate our bytes into this process memory. And how do we do that? Well, virtual alloc. And you might have heard about this function. It's pretty popular, but if you haven't, we're going to do the same thing we did with open process, so don't even worry about it. We are going to be using the extended version of the function of the API, which from the last video you should know why there's this and what difference it makes to use the extended version versus the normal version, but I'm not going to cover over that because this is already going to be long. So we can see what virtual alloc takes in, but we do need to assign it to a variable of our buffer that we want to, surgically embed into the process memory. So what we're going to do is set up a buffer for this function and note that it is of the LP void type. So let's set that up accordingly. Remember, check what LP void is, and we have it for remote buffer or our buffer. We are going to set this to now, let's look at what this is expecting. So let's fill out what we already know, and then we'll consult the documentation for what we don't. So the first parameter it's expecting is a handle to the process that we just got from here. So let's supply hprocess as our first argument. Okay, now let's take a look at LP address. From the documentation, we can see that this is inputted and it's also optional, meaning that we do not have to supply this. This is a pointer that specifies the starting address for the region of pages that you want to allocate. Now, pages in this context just means a contiguous block of virtual memory, okay? So don't let page confuse you. We can see over here that if this parameter is null, the function determines where to allocate the region. That's what we're going to set it as. Again, this isn't that important for us right now. We can just let the function determine exactly where this should start. The next one is the size of what we'd like to allocate. For this part, we actually have to start setting up our shellcode part of the program. So we will generate the shellcode later, but for now, let's at least have the variables and everything set up. So let's do. So over here, we just have a bunch of A's. We could do this with like NOP instructions like hex 90 as well, or the int3 opcode like CC, which is the debugging thing. We will just leave this semi-simple. Just know that if when we do inject this, eventually this is going to shred our process's virtual memory and it's going to make it crash because this isn't a valid region. It doesn't matter for now. And then we also want to calculate the size of this. So this is going to be the size of whatever we're allocating. We just want to allocate our shellcode. So it's going to be the size of our shellcode. So let's do that. And then this part is also pretty important. This is a allocation type. Now we're going to have to consult the documentation for this. Allocation type. So basically this just tells us the type of memory allocation that we want to use. I won't get into too much about the different ones, but the ones that we are interested in right now is memcommit and memreserve. So memreserve, as it sounds like, reserves that address space, and memcommit actually commits it, which is why we need to use them both at once. And we can use them both at once just by doing this as shown here. If you want it to be cleaner, it literally does not matter. And then the last parameter is the FL protect. This part is also very important. This is going to be the permissions of our memory. If you remember in my first video ever on this channel, we talked about why we weren't allowed to run our own shellcode after we buffer overflowed our binary. And it was because of the NX bit, or the non-executable stack, which means that even if we did get our shellcode onto there or our payload onto there, nothing would ever happen because it can't be executed. This is pretty much the same thing. If we don't set this permission properly, our shellcode isn't going to work. But you also have to remember that a random buffer of memory or a random chunk just allocated to our process, given all read, write, execute permissions, will look so insanely suspicious. And that's what a lot of things check for, because we are learning. And again, we do not care about evasion for now. We're going to give ourselves read, write, execute permission, but you don't have to. So we can see page execute read write. Instead of writing this long ass line out, we could also just write hex 40 and it'll do the same thing. Remember, it expands to this, so we literally can just put hex 40 in here because it's the same thing anyway. Oh, and if you want to see this in the documentation, you can see it here in this section. After we get to the FL allocation type, come down to the memory protection constant, and over here we can see everything. So over here, what we're choosing right now is enabling execute read write access to the committed region of the page that we're committing. Using like virtual protect, like this function, you can then later on change the permissions of this memory. You will see some attacks do that as well. If you keep on looking around, you'll see that virtual protect gets used a lot, and changing these memory protection constants is often in play as well. But with this done, we have now allocated our memory. Let's put in another print statement indicating as such. Well, first, we never actually have printed out the handle that we got, so let's also put in the statement for that and the fact that we allocated this many bytes into the memory. So we got a handle to the process, and then we're going to print a new line, and then we're going to character escape a backslash, because if you just do backslash, it's not going to be interpreted properly. You character escape it, and then we're going to print 3 dashes with the handle that we got, and then new line after that as well, just to make sure that it's okay. And then over here, so over here, we're just formatting it with the size of how many bytes our payload is. In this case, our payload is actually going to be, where's our 10 bytes. Also with this, it's also at this point that, I should probably just make a separate variable because we're using it more than once, but honestly, I don't care. Okay, let's see if this is working properly now. Let's try it. Because we want to actually get past this check, we should actually supply a legit PID. For that, I'll just spawn in a notepad. All right, and then we can use a simple. See over here is the process ID. Let's see if this works. Right, it's working. So we can see that we got the handle. This is our actual handle. So let's do that again. Yeah, so we can see all of our expected output. We get the handle. We see that we've allocated the size of the payload with the permissions, and yes. You also might be wondering, Notepad is still alive. right? It's still existing at the same PID. And I made that whole spiel about using proper bytes because otherwise it's going to shred our process. Well, the reason that hasn't happened yet is because we actually haven't written the memory in. All we've done is set aside that space with the necessary permissions. Virtual alloc is not the same thing as writing your memory in. That's what the next function is going to be doing. Speaking of which, is going to be write process memory. So let's close that and let's get started on. We can see that the first parameter is our handle. Second one is the base address. So this is going to be our allocated region, which is what we're going to supply here. And then this section is going to be our shellcode, because this over here, there's no mention of our actual payload content anywhere here. This is just a size in this buffer. Over here is where we actually write that. It's going to match the size given here as well, or here, sorry. So this is going to be our shellcode. I don't know why I chose this name. Okay, and now this is the size of our shellcode, same as this. Now lastly, let's take a look at this. This is just a pointer to the variable that receives a number of bytes transferred to the specified process. It's optional. If it's null, it's ignored. If it's null, it's ignored, and ignored it shall be. We are going to get some R buffers could be 0 here, and we could just make another check for it to see if it's null or not, but kind of redundant here. Let's print another message saying that we've actually written this memory. We are at the last step now. All that's left for us is to create a thread to run our payload space. So what we're going to do, we're going to use the create remote thread function for this one. And there's also an extended one. I think we're going to use the extended one actually. Okay, yes, look, there's like 1,000 parameters, I know, but most of them are just going to be null or 0, so don't even worry about it. The first one is going to be a handle to our process. Right, let's make it like this. Process. Second one, let's look at the documentation for the next section, which is the thread attributes. So looking at the thread attributes, probably zoom in. Looking at the thread attributes, we can see that this is just a pointer to the security attributes structure that specifies the security descriptor blah 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 blah. If it's null, the thread gets a default security descriptor and the handle cannot be inherited. We're going to set this to null. We don't care about this for now. And also while we're here, we're also going to be setting the stack size to 0. If it's 0, the thread uses the default size for the executable. And this one we'll come back to. But for now, we're going to set this to null, this to 0. So to null. This next section is a bit tricky to conceptualize. It's not tricky to implement, but we want to know what we're doing here, right? So let's go back. This parameter is a pointer to the application defined function type of the LP thread start routine. Now, okay, what is LP thread start routine? Well, let's get more information on thread proc. The LP thread start routine type defines a pointer to this callback function. So basically what this is, as best as I'm able to describe it, is you can think of the LP thread start routine as a way to specify the starting point of execution for a thread. So basically what we want to do with this thing is cast it to our buffer, because we want that to be the starting point of the thread. So that's what we're going to do. We're going to cast our buffer to LP thread start routine so that the function knows, okay, this thread's going to be created, but I want you to start execution from this entry point. Remember, we need to cast it, right? To make sure that the expected signature of the thread entry point is okay and it matches. Do that. Okay, that's the hard part done. The rest of them are pretty easy. Okay, let's go back to the documentation and see what we can cross off. So we're done with this part. Oh, and I forgot again. So we can also see that the return value of this is just like open process. If it succeeds, the return value is a handle to the new thread. Very, very similar. It's pretty much the exact same as open process, except we're dealing with threads now. So we can set up the same checks. We know that we also have to make this function hold that value. That's the reason why we also added this here, because it was for this part. So let's also assign that. Right, now back to the documentation for the rest of the parameters. Guys, we are almost there. Okay, I know. We got past the casting to the LP thread start routine, and now, like, what is that? This part is a pointer to the variable to be passed to the thread, blah, 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 blah. We can set this to null. The creation flags. Do you remember when we were doing the first video and we set the creation flags and it was like, oh, we can change the process priority? Basically what happens in this case is that if we change these creation flags, we can either start a suspended thread with a create suspended value, or this one, but we're going to do 0 because we want our thread to run immediately. That's what we're going to do. We're going to set this to 0. This is going to be null. This is going to be 0. Null. Run immediately. Okay, just 2 more. Now, the last 2, the attribute list, it's optional. We're not going to supply it. Include this, we're just going to set it to 0. And then over here is a pointer to the variable that receives the thread ID, or the TID instead of the PID. I mean, you could set it if you want to. It's up to you. If you want to set it up, you could do something like Could do that, and then this is gonna be 0 thread ID. And with that done, that's everything there. All we have to do now is set up that check to see, hey, was a valid thread handle created? So it opened, didn't that run? If not, spit out that error message with this wonderful function. So let's set that up. Also at this point, if at this point we don't, I want to close the previous handle that we have on the thread, otherwise it's going to remain open. You could have it like that, I guess, but to make our code clean, right? I say that as I have two fucking wiggles. Okay, so I'm not going to go in depth with this function. It's literally just one parameter in, and it does exactly what you think it does. So this just takes in handle object in case we want to close the handle to the process. We are eventually going to use this again down here once everything's done to cleanly close everything. That's done. Otherwise, so that check is there in place. Now, if that check is passed, we're going to say, hey, created that thread. Here's the ID of it. Here's the address of it. And at this point, it should have ran. And after that, we're going to close everything. So same thing as what we did up here. We are saying that we've got a handle to the process and we're printing out the value of it. Over here, also doing the same thing, except I want to see that thread ID. So that's what we have over here. And at this point, everything will have ran. And then what we could do, we could close the handles that we have, the two handles that we have at this point. Right, so we can see that after we've done everything, then the shellcode would have been executed. We will clean up by closing any existing handles and then exit cleanly. There's another thing that we could do right before here, but I want to run this. It's been a long time since we actually ran anything, so let's finally try this. But remember, this is not valid shellcode. This is just spam and it's going to kill our process, but if it kills our process, we'll know that it actually is working somewhat. So let's try that real quick, and I'll get out of full screen for this one. Okay, and 3, 2, 1. Wait for it. There we go. It was really quick, but it happened. Actually, we can see this better with a tool like this beautiful tool, Process Hacker. We search for the process. We can see that it spawned with a new PID. Nice little Phoenix cosplay. Let's see what happens. You can see this exactly what I was talking about. You will see it have a complete meltdown. Oh, well, in this case, it just died, but you get what I'm saying. That shellcode was invalid, and everything's working properly, as we can see here. Now it's time to use proper shellcode. However, before we do that, I also want to introduce this one new function that will wait for this thread to finish before doing all of this, and that's going to be wait for single object. So from here, we can see that it takes in a handle. In this case, we're waiting for a thread to finish executing, and the amount of time that we want to wait for. And once this is done, then we can continue with this part. So let's do. So we can say that after this is done, thread is finished executing. Let's go look at the documentation for filling in this part. From here, we can see that the timer interval, if we set this to infinite, the function will return only when the object is signaled. Now, look, this does sound like trouble waiting to happen. Maybe it is, but we're gonna do it. We know that this thread will eventually finish, right? And we know that if we close the process, it will kill the thread as well. So either way, just introducing the new API, I really want to get you guys comfortable, which is why you don't have to do this again. This part is completely optional, but I'm just gonna do it. Now we should see what happens real quick. Alright, file 8. Thread finished executing, and voila. And also, if you want to, do this. 10, 8, 2, 4. Waiting for thread to finish. You saw how it hung on for a little bit, and then there we go. Very clean. Now, everything should be in order for us to try actual legit shellcode. Who is dying in the back? I'm gonna open up the Kali machine, and I will see you guys on there. We are back. So, you will notice a lot when you start doing your own independent research. Not even just with malware development, but with binary exploitation a lot of the times, especially on Windows. Well, actually, mostly on Windows. The shellcode used, it's not always a reverse shell, okay? A reverse shell brings a lot of unnecessary overhead with it, like especially if it's heavily signatured shellcode, like what anything from MSF Venom, which is the tool we're going to be using today, comes from, right? That is heavily signatured. Any decent EDR, antivirus solution, will most likely pick it up, okay? Now, there are ways to obfuscate or alter that shellcode through things like RC4 encryption, XOR encryption, multiple different little things that you can do. But most of the time, what you might see is benign shellcode, something like a message box opening, something like a calculator opening, right? You might hear the term pop a calc used a lot in this sphere, because if you can pop a calculator, basically meaning if you can run a calculator, you can run a shell for the most part. Originally, I wanted to do a calculator payload, but I feel like because this is our first actual process injection, I should spoil you little divas a bit, and I guess we'll do shellcode for a reverse shell. All right, we have to remember, guys, the architecture of your shellcode is so important. I've had many people come to me saying that they've done everything, that the process just ends up dying and like nothing happens and nothing's working. If it's the case for you that you run your injection program and either nothing is happening, the process isn't working, the process is dying, or you can't even get a handle to the process or thing like that, check your compiler. Check the way that you're compiling it. You have to make sure that the architecture matches. So your shellcode should match your architecture. Your target's architecture should match your program's architecture. So if you're injecting into a 64-bit process, make sure that you compile a 64-bit program that uses 64-bit shellcode. Okay, this is very important. But with that out of the way, let's hit this and then copy and paste what we have from here and see if we can get a shell. But because I'm using interpreter, I'm gonna have to set up multi-handler to catch the callback. I should have done a different shell perhaps, but it's our first time, who cares? All right, so we can see what gets generated, a shit ton. That's a lot. At this point, if you try to compile and your Windows Defender is not disabled or there's not an exception path, you will not get this to compile because this is that signature. Like, Windows will automatically detect this and completely nuke your program. So make sure you have that, and let's just compile it. Okay, compiled perfectly fine. I'm gonna set the listener so I can catch this shell. This is a new banner. I don't think I've ever seen this. I haven't used Metasploit in a while. So. Is that everything? I forget. That should be everything. Let's run this as a job. And now, this is the moment of truth. We've already compiled the program. I'm going to open up Paint. Remember, the process, it doesn't matter as long as it's the same architecture. And you know, that's not protected. Some Microsoft processes are protected. Okay, so what we're going to do is see if we can do this. Find the process ID of Paint. All right, the moment of truth. All we have to do is apply that process ID. If all goes accordingly, we should be able to catch that shell. 13148. All right, 3, 2, 1. Oh. This is a really good sign, actually, if it's hanging on the thread. And look at that, guys. We get our interpreter shell open. Look at that. We are literally on the Windows machine. This is crazy. This is awesome. If it ever loads, how many... Oh, shit. Let's see if we can get a screenshot of the current of the computer. Something cool, you know? There it is, a screenshot from our current target. Isn't that crazy? Endless possibilities as to what we can do now. Really fascinating stuff. And I just shut off Kali, so at any moment now, I should finish the thread. Look at that. Awesome. Holy shit. Well, first of all, give yourself a gargantuan pat on the back. You've just done your first ever shellcode injection. Doesn't it feel great? Now, I know the video was long, but the great thing is, the DLL injection is like the shellcode injection's bootleg, barely hominoid, milk-fed little cousin, okay? I'm just joking. The DLL injection is actually pretty insane, and it's got so many applications. For instance, if you ever take up game hacking, a lot of your internal hacks are going to be using DLLs and stuff. Speaking of which, it's finally time to discuss the sub-technique of process injection. Take a break if you must, stretch, hydrate, fix your goddamn posture, stop with the protractor cosplay. Here we go. Okay, obviously first we need to figure out what DLLs even are, and why you might hear them being thrown around all the time in the Windows world. A DLL, or a dynamic link library, is simply a collection of data or executable functions that an application in Windows can use or sometimes needs in order to function properly. Okay, well, that's great and all, but why do we care about this? Can't a program just have what it needs to run programmed in it to begin with? What's the point of loading in libraries? Oh, you're so small. I want to pick you up and fling you off of something. It's so naive. DLLs, or libraries in general, right? They let several apps share the same code rather than needing to have one application have everything one at a time. As you can imagine, this is crucial because it allows stinky little programmers to modularize the shit out of their work. and share similar code amongst other applications. This can lower the size and complexity of their code base, and most importantly, save time and effort when creating new software. Furthermore, pretty much any process or application that you will end up opening is going to have at least some DLL that it needs or uses in order to work properly. That's pretty much all it is to a DLL. It's just something that an application needs. Enough theory for now. Let's just put this into practice. Let's go back to basics real quick. A quick little message box. Now, a simple message box program would be something like this. However, what if we wanted to turn this program into a DLL that did the exact same thing? It's actually easier than you might think it is. And of course, there are differences between making a program versus making a DLL, but it's not too bad. As you know, in normal executables or programs or whatever, there is an entry point or a start or a main where everything starts, like the main function in our C programs. In DLLs, they too have an entry point, but it's called differently. It's called DLL main, and it's important that we set this up properly, otherwise our shit's not going to be shipping. So let's look over what the documentation says, and at the same time, start turning our message box program into a DLL. Remember that you can also find this DLL that we're going to be making either on my GitHub repo or on my blog, but try to make your own first. You'll learn a thing or two. Okay, so the first thing that we want to do is, again, start up a new project. You can compile this in whatever. I'm going to do it in Visual Studio. I'm just going to make it an empty project. Let's call this random DLL. I don't know. First thing that we want to do, right, is first we have to go into our project settings, properties, sorry, and we have to change the configuration type to a dynamic library, DLL. Okay, now let's take a look at what a standard DLL looks like. So from the documentation, we can see that this is what a standard example of a really simple DLL looks like. This is the main of that DLL that we have to define, right? This is what it must follow. And then over here, we have a bunch of various different cases for what the DLL should do depending on what happens. So we have a bunch of switch cases. So DLL process attached. Basically, whenever a process loads our DLL, we're going to run whatever's in this case. Let's copy over this main, and then we'll talk about the individual parameters. For now, it's very simple. It's basically just depending on what happens, we want our DLL to do something, right? And you can have it calling in functions, or you can set up the code directly in these switch cases. It's all up to you. We're making a message box, so we can literally just have a message box function whenever our process attaches, which is what we're going to do. All right, so again, because this is a DLL and we're going to be working with a bunch of Windows shit, we're going to have to include the Windows header, so let's just do that. So we can see the DLL main entry point, or the main function of this DLL, is an optional entry into a DLL. The system also calls the entry point function for a DLL when it is loaded or unloaded using the load library or free library functions. This is what we use to load up our module. Let's just copy this. So over here, this is the handle to the DLL module. I don't like this. I remember when in like the first video, we skimmed over it briefly, but we said that aside from processes and threads, you can also get a handle to modules as well. This is pretty much what we're doing here, creating the instance for that handle, H module. Now this part is what we're going to be using to check to see what the reason for the calling function was. Basically saying like what happened in that process that called our library or DLL, and based on what happens, we can run the switch cases for that reason. And this last one is just reserved. Some functions will literally just have a reserved parameter like this, and it's just reserved and it has to be there. And going back to the H module thing, the thing is, why would we even want to get a handle to these DLLs? Like, what's the point? Well, if we get a handle to a DLL like kernel 32, so if we look over here, we can see the kernel 32 DLL, or module, library, whatever you want to call it. It has a lot of these functions, right? And these are just functions that we can use, and we do use some of these. There's create process, there's create remote thread X. So all of these functions that we've been using, they reside in this DLL in kernel 32, and it allows us to interact with the operating system. So if we get a handle to this module, what we could do is look inside of that library and try to find addresses of these functions, try to find these functions so that we can use them, which is what we're going to be doing with the DLL injection. We're going to get a handle to kernel 32 to look for the load library function. If we remember, load library is just going to take in one argument, which is just the name of the library that we wish to load, or whenever a thing is loaded, it's going to call the entry point of a DLL. All we have to do is use load library to load in a library, and the DLL main will automatically get executed from us. Let's go back to programming. A little bit of a tangent. Don't get too worried if you don't understand it all yet. I'm providing the background now so that when the code part comes in, we'll understand it better. Let's fill out the rest of the main. Now we're gonna have a bunch of switch cases for our reason. Don't like this at all. Just gonna call this reason. And we don't have to include every single one. If we copy the syntax, good lord, copy the syntax from the documentation, we see that there's a bunch of this bloat. It's everywhere. We don't need any of this. We can just have our DLL do it for whatever we really want to do. So in this case, we only really care about the process attach. Whenever a process loads our library, our DLL, we want it to just run whatever's in this case. And remember, this is, this is where you would be malicious with it. You can put in whatever here. Get rid of all this. Alright, so in the case that a process attaches our DLL or our DLL gets attached to a process, we want to create a message box. That's what we're going to do. So we should be able to compile this now. There is a way for us to actually call this main function or any functions within DLLs by using a tool called if it ever fucking loads. Why is... So, and it is important sometimes to figure out what valid functions a DLL contains if you want to use it in your attacks. For instance, if we want to do a DLL proxying attack or sideloading, we want to proxy over those functions, because if you think about it, if some of you may have done a DLL hijack or some sort of unquoted path thing or something like that with DLLs where you replace a legitimate DLL that a program uses with a malicious one. But if you do that, the process, sure, it will load the DLL and your code will execute. If the function that the process needs to function isn't present within the DLL, it's not going to work properly. So that's where the DLL sideloading and stuff comes in. You find out these actual functions that are present within the DLL, and then you can export them and proxy them over, and it's really, really cool. A bit too crazy for us right now, but it's just nice to know that it exists. And so the way that you can run these, say we wanted to run DLL main, using a tool like run DLL32, we have to specify the DLL name, and then specify the function that we want to run, which in this case is just going to be DLL main. And we will get an error, but it will run the code. So let's try that. And there we go. We saw that. It runs exactly this. And now after we press this, it's going to error out. There we go. That's pretty cool. We have just generated our first DLL. Give yourselves another pat on the back. Good job. So what I'm going to do now is move this DLL into a place where it's going to be easy for us to reference later, because that path, that /64, debug, all that shit, that's just incredibly insane. Okay, so there's our DLL. I'm just going to move it to maldev. So there it is. Let's move on to actually programming the DLL injection. I will program most of it and come back when there's something different from the shellcode injection part, but for the most part, it's going to be the same thing. But I will stop to talk about what's different when that part actually comes. Until then, just enjoy me mindlessly smashing away at my keyboard. Just going to do another empty project. I'm actually going to set up my status symbols properly this time. I cannot believe I went that entire time without even noticing that they were all the positive symbol. Okay, yeah, so now it's set up properly. K for OK, E for error, I for information. I'll set up everything and then I'll come back to what's different. Most of this stuff is extremely derivative. We literally just covered this in shellcode injection, so I won't talk about that. I also put this message down here, which makes more sense because in the last one, I had the message here. And so even if we did supply a false PID, it would still try to print this out. It's better to have it here. Okay, so remember when I said that we needed to get a handle to the module? Well, there's another type for it, for handles to modules or DLLs or libraries, and it's just called HModule. And we're gonna do it for the kernel 32 DLL, which we discovered was responsible for most of these functions to begin with. So we're gonna get a handle to that module. Okay, so that's the first different thing. Secondly, we want to actually specify the path, the full path of where this DLL is for the load library part. You can also limit it with this if you want to. It's up to you. Where the hell did I put this DLL? And make sure you also character escape. Alright, cool. And we also need to get the size of this. It's like getting the size of our shellcode all over again. And now, it's just business as usual. I'll come back once again if there's something different that we need to talk about. But for the rest of the part, it's the same process. We're going to allocate write to the process memory, and then we're going to get a handle to the module, which is what we're going to come back to. Now for this, we don't need page read write execute. All we need is just to have read write at this point. We're not really executing our shellcode, but we need to have the ability to read and write onto the memory into this buffer. So we're going to put up read write. I should have mentioned this in the shellcode injection part, how virtual alloc isn't the same as actually committing that memory in or writing contents of it. You can think of this section here, think of our buffer as sort of like a canvas, right? It doesn't have any contents of what we want to allocate in it, but in write process memory, we're like, okay, write this section to that canvas that we just made. It's got this size, it's got all of these permissions, you know, we want to write our shellcode, so we can write that content of whatever we want to write into this canvas, into this thing that we set aside for it. So just think of it like that. And of course over here, we're going to put in the DLL path, size. And I mean, I could get rid of that R buffer check. It's the same check we're just making because virtual alloc will return null if it fails. So we could just put in another check like this to get rid of this annoying ass error. I mean, I guess let's just do that. Okay, cool. So squiggle gone now, that end of this check. Okay, now this is where it's going to get a bit different. So just like with open process, how we're trying to get a handle to a process, or we try to get handles to our threads, we're finally going to try to get a handle to the module that we want to hook onto, which is going to be kernel 32. So we can do it like this. We can do it using the get module handle function. So let's write that out and then we can go to the documentation to take a look at it. We can see that it literally just takes in a module name. And because we're trying to get a handle to kernel 32, we're going to specify kernel 32. And because it's a wide function, we have to make sure that we encode it as such. Let's take a look at this real quick. So get module handle, it retrieves a module handle for the specified module. We want to specify our DLL, it's going to get a handle for the DLL, and all it takes in is a name of the loaded module, either a DLL or an ext. And if we don't specify an extension, it's going to, by default, try to do .dll. Be sure to use backslashes, not forward slashes. And we can see, just like open process, if the function succeeds, the return value is a handle to the specified module. If it fails, it's null, and we can combine it with that wonderful get last error function. So let's set up our checks. I guess we could try doing this with ternary operators or whatever, but that's like nerdy programmer shit, and we're not nerdy programmers. Make a macro at this point for all of these checks, or like a function. And at this point, because we have handles to our processes open, we also want to close them at this error point. And otherwise, if this check is passed, that means we would have got valid handle, so we can print that handle out and we can let the user know. Okay, now this part's going to be a little bit tricky, but just follow along, you'll get it. At this point, we would have gotten a handle to our kernel 32 DLL, and because of that, what we want to do now is reach into that module, basically, and then find out where one of these functions that we need, which was load library, if you remember, where it resides. And once we get the address of that function, we can use it in our create thread to run it. And remember, a load library literally just takes in the name of a DLL or a module and it'll just run it magically, wonderfully. And so just bear with me, I'll program this line out and then we'll explain it. Alright, so what are we doing here? Because we're going to be using the address generated from this in our create thread, remember it has to follow that signature, which is what we're doing. We're typecasting that. The result of this for later use for the create remote thread. Remember we discovered what LP thread start routine even is. It just tells a thread where to start. Now this might be pretty obvious, but what this function does is we give it a handle to a module, so like kernel 32, and within that module we'll look for a function or a procedure name, and it will spit back out the address of that function. That's pretty much all it does, and because we get the address back, we can typecast that address return to a start routine. So when we create our thread and we give it this, it will take that load library that was outputted from get proc address, and it will load and it will run our DLL path. Let's print out a message with the address of load library. And now it's just a matter of creating our thread. Everything's set up at this point. We don't really need the extended one for this one. We could just use create remote thread. And remember, we typecasted that start address already. It's gonna run this. So otherwise, we'd have to like do something like this, and it'd be like, what the hell? Just do this. At this point, we can just wait for the thread to finish. And in this case, the thread's only going to finish once we press the message box. Once we press OK, it's going to complete, and then that's when the rest of this code will cleanly exit. That looks like everything. We should finally be able to run our injection now. Let's give this a try. Please no errors. Oh, thank God. Now there actually is one caveat to using load library, as discussed in Open Security Research blog. Like, I can't say this name, but amazing dude. The major downside is that, say we run this load library thing and it loads in our module once, it's not going to execute it again if you try it. That's one caveat. I mean, you can get around it by closing the process and restarting it and doing it like that, or like doing something else. But again, like Brad said, it's more code. All right, cool. So now let's actually try to run this. Hopefully if we run this, we should see that our DLL gets loaded, our message box should appear. So 3, 2, 1. Oh my god. Oh, look at that. It's so beautiful. Right, so everything's working. So we can see we got the handle to the PID, allocated our that buffer. We made that buffer with the read-write permissions, and then we wrote in the DLL to that buffer. Got a handle to kernel 32, which resides at this address, and then we'd see that we reached into kernel 32, spat back out the address of load library. And then we got a handle to the new thread, the new TID. And now we're just waiting for this to finish. So you'll see that once we finish this execution, or the program should finish. What's happening? Oh no, it finished when we closed the message box. It just command shell was getting DDoSed or something and taking forever. I want to run this again real quick just to show you guys what happens in the actual memory if we look. It's really, really cool. Okay, so, alright, so just did a quick little self-portrait. Alright, here we go. Let me show you this. So we're gonna run this. Alright, that's gonna finish. There we go. So, and now if we go look at this process within Process Hacker. So yeah, if we look at, what was the PID? I mean, we could just search for PID. Right, so if we double click on this, we should see our DLL here. Look at that. So we can see it being used here, right? And a thing you'll notice is, firstly, modules. We can see in the modules, whatever the modules this process loads, we can see our custom made DLL in here. It's been loaded, right? It's unverified, so it's very easy to detect against these things, obviously. Like, we can just tell right away, unverified. Whereas if we look at something like a legit DLL, NTDLL, it's verified by Microsoft, right? And NTDLL is huge. It's going to be a huge surface area for us to attack later. But random DLL, and we look at all the we can look at all of these imports by it. We can see the message box. You can see our imported functions. This is where we created that message box function. Do you remember? And if we look for like strings, I promise I'm not crazy, dude. Where is it? Where is it? There, okay, shit. Yeah, so we can find, look, we can see the LP, whatever the parameters for message box was. I think it was LP content, LP title or whatever. We can see them here. Look, the who goes there title, that's crazy. They can literally like read that in from the memory. But yeah, that's literally all there is to this DLL injection. If that was something malicious, again, it's super easy to just make a reverse shell thing for our DLL. We would have just gotten a shell. But yeah, guys, you guys just did shellcode injection and DLL injection. This is humongous. Congratulations, guys. So here's the hubbub. I will briefly talk about some things I've seen in regard to these exploits and where some people can go wrong, but this will be pretty surface level since if you follow this video, my blog, or the plethora of other better resources on this, you should be able to get this working with little to no hassle. If you want to see these pitfalls more in depth, then head over to the blog where I'll be writing more about them. Okay, so we've mentioned this like 1,000 times, but compiling the right architecture is so important. We've gotten tons of messages telling us that the program spits out all the expected output, but it doesn't create a handle for a new thread, a new process doesn't spawn, or the target process crashes, etc. And as we've discussed already, this is most likely an issue with the way you're compiling it. Each compiler has its own pros and cons. You use whatever you want. I just use MSVC. But learn your compiler. Make sure you're compiling your program with the architecture of it and the target process in mind. Remember that some processes are protected by Microsoft, and as we saw, if that's the case, then some of our access rights will be prohibited. Also remember that you're limited to what you're able to attach to. You can't get a handle on an elevated process if you don't possess those elevated rights. Make sure to have an exclusion path or disable defender while creating this, otherwise it'll obliterate your program. You can mess around with encrypting your shellcode. Zora encryption is a big one, but if you're doing this, remember to use a relatively large Zora key, since some EDRs or whatever can actually brute force these super small 1-character keys that people keep using. There's also AES or RC4 or whatever, but that's for you to go and try to implement. And that's just about the gist of it. Let's close out this video now. Thank you so much for the attention that the first video has garnered and for the residual following that ensued because of it. I am eternally indebted to you guys for taking the time out of your day, spending hours watching my content and internalizing it by implementing it yourselves or just sharing it, commenting, liking, subscribing, etc. All of this came quite literally overnight, and so I'm still obviously trying my hardest to adjust and maintain all of this. I say we a lot in my videos, but this is a single-man operation. It's just me, and as such, these videos take a lot of time and effort to make. But again, your guys' responses to these videos make all of the gray hairs, sleepless nights worth it all so much. So thank you so much. In the next video, we'll be taking a look at the lower level NT API from NTDLL and perhaps some direct system calls as well. Although I'm going to be taking a short break from making content since this video took a lot out of me to make, but rest assured, Maldev Part 3 will be out. Anyways, thank you guys for watching. I hope you learned something, and remember to be responsible. Check out the Discord server, blog, and all that stuff out in the description. And until next time, goodbye.